Hey guys, so today we're going to be talking about how to approach a problem with polyprotic acids. So polyprotic acids are essentially when you have more than one hydrogen attached to a compound. So instead of HCl, which is monoprotic, it only has one hydrogen, you have something like this, absorbic acid, which is H2C6H6O6. So you have more than one hydrogen that you have to dissociate. So what this essentially means is that you have to dissociate this acid more than once. You have to get rid of one hydrogen, and then you have to get rid of another hydrogen. So you have to do two dissociations to get a complete dissociation in order to solve for the pH. So because this problem takes a little longer than it does for monoprotic acids, I decided to already kind of draw out a couple ice tables for both dissociations and write in my initial values in my initial work. So I'll go through my thought process here. So absorbic acid is H2C6H6O6. So in order to dissociate that, you will create HC6H6O6 minus because you got rid of a hydrogen and an H plus ion. Now we know initially, which is what the I stands for, initially we have 0.014 moles per liter of absorbic acid. And in our beaker, before the reaction occurs, we know that we'll have 0 moles per liter of product. We'll have 0 moles per liter of our H plus ions and of our HC6H6O6 minus. Now, the change that will occur when this reaction takes place is that our absorbic acid, we'll be losing some of our concentration of our absorbic acid, and we'll be gaining some amount of product. Okay, so our equilibrium end expressions are going to be 0.014 minus x and x and x. Okay, so 0 plus x will yield x and x. So now we have to write out our equilibrium expression. So what's kind of unique for polyprotic acids is that we don't just have a Ka value, we have a Ka1 value, a Ka2 value, and possibly a Ka3 value if it's triprotic, if there's 3 hydrogens. In this case, we only have 2 hydrogens, so it's only going up to Ka1 and Ka2 because we know that there are 2 dissociations, so we have to have 2 K values because we have to do 2 ice tables. I know it sounds confusing, so let's go through it. So here we have the Ka1 value, and they give it to you to be 7.9 times 10 to the negative 5 equals x squared, which is your product, over your reactant, which is 0.014 minus x. Now, usually in any problem, in any acid base or any equilibrium problem, you would try to do the 5% assumption method, which is just putting 0.014 here and getting your x value and finding a percent from your initial concentration and hoping that it'll be less than 5% so that your assumption can be verified. Now, because I did this problem before, I found out that our x value will actually yield a percent that is higher than 5%. It's going to be about 7.8%, which is pretty high. So our assumption won't really work out. So I took the liberty to do the quadratic behind it because that's the second way you can do it if the assumption doesn't work. So I multiplied it out. I did 7.9 times 10 to the negative 5 times our expression below equals x squared. So if you bring the x squared onto this side, it'll be minus x squared. If you multiply it out, if you FOIL this part out, you'll get 1.1 times 10 to the negative 6 minus 7.9 times 10 to the negative 5 minus x squared equals 0. If you use the quadratic formula, if you have a quadratic formula program on your calculator, you'll get x to equal 0.0010. And if you do the assumption, you'll get an x value to be 0.0011, which is not a huge difference. So I guess you could get away with the assumption value, but why not be safe? If the assumption doesn't hold up, just do it the long way. It's better safe than sorry. So we get an x value to be 0.0010, meaning we know that our concentration of HC6H6O6 minus will be approximately 0.0010. So I guess I could erase this and erase this and type in those new numbers or write in those new numbers. So 0.0010 for my molarity here. Same thing over here. And also I can get a new molarity for my product at the end of the reaction. I know that we lost x from our 0.0014. So I'm going to kind of do 0.014 minus 0.0010, and I would get a value of approximately 0.013 moles per liter. So I got my new concentrations at the end of the reaction. So now I have to carry on whatever work I did over here to my second dissociation. And I'll show you what that means right now. So my second dissociation will start where this left off. We'll start off with this ion, which we're going to get rid of our second hydrogen in this dissociation. So we have HC6H6O6 minus, and we dissociate it into an H plus ion and a C6H6O6 2 minus ion. So what do we have initially? What do we have initially of this HC6H6O6 minus? Well, initially we don't have 0 moles per liter. We actually have a certain amount. We actually have 0.0010 moles per liter. Okay, so that's very important to know, that we brought this value that we did from our first dissociation into our second ice table. That's what makes polyprotic acids very unique. How much H plus ions do we have? Do we have 0? No, we don't have 0. We have to carry on whatever information we got over here to our second ice table. So we have 0.0010 moles per liter of H plus that carries on from our first dissociation, excuse me. So how much C6H6O6 2 minus do we have? Well, do we have any concentration of C6H6O6 2 minus that we accounted for in this ice table? No, we don't. So we know that we'll have 0 moles per liter of our 2 minus ion. Our change will be the same. We'll be losing some of our product, or some of our reactant, excuse me, and we'll be gaining some of our product. Okay, so plus X and minus X. So our expression for our end reaction will be 0.0010 minus X and 0.0010 plus X and 0 plus X, which is just X. So we'll do our second equilibrium expression. We'll do Ka2, and the 2 denotes our second dissociation, and our Ka2 is given to us. Our Ka2 is 1.6 times 10 to the negative 12th equals our product over our reactant, which is x squared, or actually, excuse me, it's not x squared. it is x times 0.0010 plus x over 0.0010 minus x. Now, as I said, I did this problem before, and I did the assumption again, and if I did the assumption, I could simplify it into x times 0.001 over 0.0010. Because I made the assumption, the 5% assumption here, meaning that the K value is so small that the change, this minus X and this plus X, will be so insignificant that it will be very close to our initial concentrations. And surprisingly, our X value yielded a value that was lower than 5%, so you'll just have to trust my word on it. So this assumption is valid. And what we can do here is we can simplify it. We can do 0.0010 to cancel out these two values, and we can get our x value to be equal to 1.6 times 10 to the negative 12th. Okay, 1.6 times 10 to the negative 12th. And if we do this, 1.6 times 10 to the negative 12th, we can solve for our concentration. We can solve for our concentration over here to be 0.0010 plus x. So 0.0010 plus 1.6 times 10 to the negative 12th. And sorry, I have to type this into my calculator just like you guys are, I hope. And I get a H plus concentration of 0.001. Same thing I can do for these guys, but I'm asked for pH, so I really only care about my H plus concentration. And if I do the negative log of this H plus concentration, which is 0.001, to get my pH, I get that my pH is going to be approximately 3.0, and because I have 1 sig fig here, I should only put 1 sig fig, but because our K value has 2, I'm going to put another sig fig here. So our pH would be equal to 3.00. 3.00. And I know this part might be a little confusing if you don't know the assumption method. If you have watched my previous videos, then you definitely know the assumption method. If you have done chapter 13 chemical equilibrium, you definitely know the assumption method. But I did the assumption method here. They both yielded less than 5%. So I got my X value. I plugged in my X value into my H plus expression. I got a new H plus expression, and I got my pH to equal 3. And the reason why I don't have to add this H plus concentration to this is because this ice table has already taken into account the initial concentrations that were founded in this dissociation. So this second dissociation will yield all the H plus ions we have in our beaker at the end of the whole reaction. So our pH would be 3.00. Thank you very much for watching this video, and I hope that it's been very informative.